Hi and welcome, and join us for looking at space, and we're going to start off with the solar system. Now the solar system is obviously the closest to our home, and during the next few lessons we'll be looking at a combination of what goes on in our solar system and how that is reflected in other places in our galaxy and then the universe. And there's a lot of stuff we don't know about the universe and things that we use our own solar system as a basis. So if we can understand our own solar system, we tend to be able to apply that to other places. So if you're very clever at taking notes, you'll probably find this circle a great place to start. Writing the solar system in the center gives you a nice place to put all the key terms. And if we were in class right now, I would be asking people to write down all the things they know about the solar system. And one of the very first things that comes out is planets. Now I'm going to put planets on the side there, and we're going to leave some space, because in a second we're going to have a look at all the planets and putting them in the correct order. And here's an opportunity to write them in nice and easily. Other things that you would normally be discussed is we'll look at the sun. Now in a further lesson we're going to look exactly how the sun is created and how the lifespan of suns works, but we're going to keep it to the simple bits now that there is a sun in our solar system, and there is only one of them. Other things in our solar system, we have things like asteroids. Okay, we have lots of dust. We have ice. Obviously, we've covered planets. Now, planets formed from all this leftover dust. Now, the solar system starts with the sun, so you might suggest, why isn't that where we're starting? Well, the sun's quite a big part, and we need to have a look at all the little bits left over to understand where it all began. So asteroids, dust, ice, and there's a few other things we're going to add as we go along in this lesson. So there should be plenty of space to add in more key terms, and when you get the opportunity to put explanations outside the circle, they're obviously really important. That's a good place to write them. Okay, so in the lesson we need to walk away with the structure and contents of the solar system, which we've already started on. We've already started identifying those key parts, and if I was bouncing around the classroom we would probably get a dozen or so of them, and we just really need to understand why they're there. We're going to have a bit of a history lesson, how the ideas of the solar system have changed. So we now have a model of our solar system. We understand very much the path and where our planets were. But if we go back a few hundred years, so even as far back into the 17th century, we still didn't quite understand how our solar system was structured. And we're going to have a little bit of a look at how religion was involved in some of those decisions. We'll try to keep it very science-based, but it's important that we recognise where science and religion didn't always agree, but usually came to a compromise. And the third one, we'll just have a look at explaining investigations of our universe. Okay, so there are three fairly easy parts, and if you've got a decent piece of paper in front of you, decent size, or you're using a whole page in your book, you should be able to get most of the notes from this lesson on that page. So the very first place to start is with the planets. And one of the things I'd like you to make sure you're adding on, let's get my pen back, is when we had our little circle map at the start, and I got you to write solar system, and I got you to put planets out here, and I said you need to leave some space. We need to write these all down. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. There we go. So there are 8 planets you need to learn, and you need to have them in the right order. So please pause the video, make sure you write them down, and write them down in the correct order. Now this bit underneath, so if you're writing while I'm talking, great, it means you don't have to pause the video. Is this the scale? Now I think most of you will recognise that it's probably not. It would be a little crazy if we were this close to the sun and all the planets were squished together. If we were trying to draw our solar system to scale, we'd need about the back wall of about 4 or 5 classrooms, and that would only be if the sun was the size of a basketball. So our solar system is pretty big. And to give you some idea of how big it is, so here is Earth, here is the sun, and this distance here is 1.5 times 10 to the power of 11 meters. What does that mean in real world? No one would really recognize how about I change it to kilometers? 150 million kilometers. So it'll take you a while to drive. takes light travelling at the speed of light just over 8 minutes to travel from the Sun to Earth. So it's a very long distance, but actually it's a really important distance, because sometimes you'll hear or read about anything to do with space and that Earth is in the sweet spot. By that they mean if we were any closer to the Sun, it'd be too hot. If we were any further away, we'd be too cold. So Earth has formed in exactly the right area to allow life to set on Earth. So hopefully by now you've written on all the planets in order, and we've got a little bit of an idea of scale. Okay, so this is where I introduce something that we can use across a few lessons, because it's quite important that we recognise that we haven't been around since the start of the universe. In fact, our solar system is basically about a third of the life of the universe. So if we get a line from one side of your page to the other, and we're going to put key points along that line, and we'll give them some dates. So over the next couple of lessons, we're going to add to this line, and the first thing we need to do is we need to start off with this point in time, about 13.8 billion years ago. Now this figure does change slightly. We've had some more data come in from a new satellite that's been put up, which is like a big telescope, and it measures how far away the furthest stars currently are and gives us some idea of if they've got that far by now, how long they've been travelling for, and gives us a time. So like I said, roughly about 13.8 billion years old. Now, that's not very important to us, except for about 4.6 billion years ago, our Sun was born. Now, in between here is probably the most interesting bit, because it's quite likely all the material that made up our Sun and our planets was formed into other suns and planets before this point, because solar systems come and go, and particularly in the early times, we didn't get a lot the first 500 million years, but after that we got these really quick cycles. Suns would be born very quickly, they'd be really hot, and they would burn very, very brightly, very quickly, and then run out of energy and collapse, wiping out any planets. And that cycle just happened over and over and over again. So it's quite likely all the particles that make up us have been particles from other planets and other suns in the past. So what happened 4.6 billion years ago? Well, we'll have a look at the Sun in further detail later. But more importantly, it took some time for our planet to cool down, start to form. So all the dust that was left in our solar system starts to form into planets. And if I could draw us as a dot, it would be too big. So in the history of, there you go, there's my little dot for you. In the history of human beings being on Earth, that's too big a pixel. We're tiny, we're only just really recently arrived. We're doing a good job of ruining it for the planet, but we can probably learn from our mistakes, hopefully, before we destroy it. So that's the timeline of the solar system. Like I said, we're going to add some things to it as we go. So contents of the solar system. So when we talk about the Sun later, I'm going to talk about an explosion occurring. So let's imagine our explosion is here, and all sorts go flying out in every direction. Now, thankfully, if I threw a handful of marbles into a pit, a round pit, what would actually start to happen is they'd all start to travel in one direction. Anything traveling in the wrong direction would just get knocked by all the others. So eventually our planets start to form, and the first one to form was probably Jupiter. So I'll put Jupiter out here somewhere. Okay. Now Jupiter started forming first, and is the Hoover of the solar system. And by Hoover, I mean as it travels around, depending which way you're looking at this, as it travels around, it was just collecting all the bits of dust and ice and rock and gas, lots of gas, that was expelled from when the Sun was created. Now that's important because Jupiter is so big, it's actually one of the reasons why Mars is so little. Okay, so Mars is about 15% the size of Earth, and that's because Jupiter stole all its material. So I just want to quickly draw our 4 in, and I'm just going to break them into two halves for us. So there's Mars, there's Earth. I'll draw it a little bit bigger, not quite to scale here. Jupiter would be a bit bigger than that in this scale. We've got Venus, which is roughly the same size as Earth, and we've got little Mercury. So I'll put M Merc. Okay. Now, what's important here is these are terrestrial planets. We call these terrestrial planets, not extraterrestrial, terrestrial planets. Basically, it means they're made from rock, which is a little bit simple in the way it's described. But terrestrial planets are mainly rock-based. So our core of the Earth is metals and rocks. So a combination of two. When we go further out this way, and this is important for understanding why these planets are so big, so I've drawn that completely out of scale. So Saturn is not bigger than Jupiter. Let's make Jupiter bigger. There you go, Jupiter. Make you a bit bigger. These four out this way, so Jupiter, Saturn, Uranus, and Neptune, okay, are all gas giants. So that's meant to be an arrow. And I'll label this as gas giants. There we go. So we've got four inner planets that are known as our terrestrial planets, made of rocks and metals, and our gas giants, which do have some solid subjects, solid parts to them, but are mainly gas. So they're our gas giants. So our contents of the solar system, if I asked you that question, I'd be looking for dirt, dust, gas, ice, all those things that make up a good planet. Okay, so these are one of the problems when we ask people to start describing things about space, is they write they're correct but very simple answers, and we need to improve them. So instead of saying the solar system is made of stuff, we don't want the word stuff in science anywhere. Okay, we want to be talking about it's made of ice, dust, rocks, planets, you name it, and all the ones we've already just covered. It came from a big explosion. Okay. Can we improve? It came from a big explosion. It came from when the sun was formed. Straight away, anyone reading that is going to know this person knows what they're talking about. Even though it was a big explosion in some respects, we don't want to be too adjective based when we're trying to answer things for science. It spins around the sun. Okay, there's a few problems with spins. Okay, the two problems I have with spins is the Earth spins every 24 hours, and we do travel around the sun, but the better word for that is it orbits around the sun. So we talk about orbits when we're talking about planetary bodies. Okay. So I did say there would be a little bit of a history lesson here, and we've had some different models over the time of what the solar system looks like. Got to bear in mind that we didn't have telescopes for thousands of years, and so we were looking up at the sky, and we quite understandably made predictions based on what made sense to us at the time. So Ptolemy, who is this gentleman here, who was a mathematician, chemist, and all sorts of things, provided the geocentric model. Okay, now geocentric, please write that word down. So add it to your little circle map, geocentric, and then put a little explanation. The Earth is in the center. Okay, so the Earth's in the center. Now, as you can imagine, that made sense. If you were on Earth and you didn't know there were anybody else anywhere else other than on Earth, you would expect, hey, we're pretty important. We must be at the center of this universe. Okay. Now, there were some slight problems with that. Mathematically, it didn't quite work. And along came Copernicus. So in 1473, he was born. That wasn't the year he did all this work. He was a little bit older than that. And he proposed the heliocentric model. Okay, so the heliocentric model, so write that one down as well. Heliocentric. And this changed things. This put the sun at the center. And he described that the sun was at the center and the Earth was traveling around the sun. Mathematically, this made more sense. Because if you watch the planets long enough, you'll realize The only way it works with a geocentric model is if we're all traveling in these very strange figure-of-8 patterns. Well, that didn't make any sense. Nothing on Earth traveled in a figure-of-8, but a circle did. Slight problem for Copernicus. Everyone had got used to the geocentric model, including all the churches. After describing that Earth was no longer at the center of the universe, the church decided to issue a warrant for his execution. He was rather unpopular, so it was a bit of a dangerous thing being a scientist back in the 14th century. No, that's the 16th century when he did that. But again, he stuck to his guns. He lived out his days. You'll be happy to know he wasn't caught or executed by the church. But it did start a process of understanding more about our solar system. Clearly, we were still trying to understand a lot about our own Earth. And along came someone you're probably more familiar with, Galileo. Now, Galileo had one big advantage over everybody else, and I'll talk about that in 2 seconds. But he found the evidence. Now, the hardest thing when you come up with a new model is to prove it. And there'll be a lot of people who don't want you to prove it, who are happy with what they had. So hence the church was happy with the geocentric model. And they didn't really accept the heliocentric model for hundreds of years. But what Galileo was clever enough to do was to start collecting evidence. And that's what good scientists do. So there are 3 names I'd like you to add to your circle map right from the start. Ptolemy, so the P is like a little P, Ptolemy, who we'll talk about and link that to the geocentric. Copernicus, who gave us a heliocentric. And Galileo, who found the evidence to support Copernicus's model. And he also found moons around other planets and corrected some of the orbits. So some of the orbits that Copernicus had hypothesized weren't quite correct. Now, what allowed Galileo to do this was really simple. He's the gentleman that invented the telescope. Okay, so next to Galileo's name, could you please put in brackets telescope? Without that man's discovery, and there are many others that he's responsible for, we wouldn't have anywhere near the understanding of our solar system that we currently do. And of course, we still build big telescopes that we send up into space now. Same principle, using light and different radio waves. So that's a little bit of a history lesson. That's how we've got to where we are, and we shall go on from there. So our current model, so what we deal with is we have 8 planets, which we've already covered in quite detail. We have 5 dwarf planets. Now this also includes Pluto. Everyone always asks, where's poor Pluto gone? Pluto was a planet, but they decided it was too small, so it had to be a dwarf planet. There are literally thousands of comets, some that just remain inside our solar system, and there are some that travel far outside our solar system and come back in on a regular basis. Halley's Comet, for example, last seen in the early 1980s, travels every 70-something years, so you should see it all in about 30 years' time. I'd like to say I could see it twice in my lifetime. That would be nice. There are literally millions of asteroids. In fact, some of them are so big that we're concerned that what happens if they hit the Earth, and we're trying to map them. And from time to time, some of them get quite close to Earth. Occasionally, some of them hit. That's a question about dinosaurs for a different lesson. Now, this part here catches everyone out. When I say how the planets move around the sun, everyone goes circle. Bad news is none of them are circular. Because there's lots of things pulling on different things. Different planets pulling on different planets. The correct word to use, and could you please add it to your circle? Elliptical orbits. The most circular, so the closest to a circle in the solar system is actually Earth. It's the closest to being a perfect circle. But it's not quite perfect. Because we revolve around the sun, but the other planets pull on, particularly Jupiter, pull on us as well. Now, I'd like to introduce this term as well. Natural satellites. Okay? It's a very clever way of saying moon, which sounds like I'm complicating something really simple. It's because there are man-made satellites as well. So we talk about natural satellites and man-made satellites. So please add those to your circle map so that we don't get caught out by any of the terminology. We have one moon, and some planets have many moons. Mars has 2 moons, for example. So you're not expected to know how many moons on each planet, GCSE, but you are expected to understand that they're natural satellites, and they are not following an orbit of the sun. They're orbiting their own planet. And that's pretty much it for understanding the basics of our solar system. So if you were doing this in class, I get you to shut your books, and you can do this at home now. Pause the video if you need to, and you need to be able to name the planets in order from the sun. It takes a bit of practice. You might need to also be able to answer this question: why might we put telescopes in space? So what's the difference between having a telescope on Earth and then putting the same telescope in space? And without giving it away too much, think about what the atmosphere does to light. And what are the 6 types of bodies in the solar system? So bodies, so we're talking about celestial bodies, so what kind of things in the solar system. If you can name all of those and do it consistently, you're in a very good place to understand the topic of space. Good luck, and I'll see you in the next lesson when we'll talk a little bit more detail about the sun.